vocabulary, units, customer separate, which I appreciate. Sincerely. That's your three dots, multiple choice. I gave you the multiple choice sheet, but I did the question, so that was, not really helpful. So thank you for that. All right, take one more minute, and we're going to kind of recap these as well. The vocabulary is heavy. It's a dense set of vocabulary. So that's why we need to talk the same language. That's what I want you to read. Oh yeah, unit 2 test corrections. Thank you. All right, guys, let's kind of jump in all feet because thermochemistry is the next one, obviously the next big idea. So we've gone from we know how to write reactions, we know how to do stoichiometry, we know that chemical changes happen and sometimes chemical changes exist, emit gases, which is the gas evolution. Well, sometimes chemical reactions cause heat exchange, right? So the heat exchange component is really what we're honing in on. But not only something's getting warm, please stop talking to your group general, thank you. Not only something getting warm or something getting cold, but we're now quantifying it, right? And we're quantifying it in relationship to a measuring device that we just happen to have that we use to measure temperature, that we use to measure energy exchange. So can we measure heat exchange? Yes or no? Give me your gut. No, we cannot measure heat exchange. Heat, I don't have anything that measures heat. What device measures heat? Nothing. What does a thermometer measure? Temperature. You see there's a difference here. So that difference means that we have to go around the world to find, go around the bush or go around whatever to collect data and use the data to find heat exchange or to quantify heat exchange. So there's a difference there. And so that vocabulary that describes all these pieces has to go together very smoothly so that we're talking with the same language. So when you use the term, you need to be actually understanding what that term is so that you're using it correctly. So this background information, thank you for some of you guys for annotating, highlighting, writing down questions. The information that you're reading can go in one ear and out the other, right? You see it. Some of you guys have photographic memories. I am not that person, but I know I wish it would make our lives so much easier. But if you know that reading it is not always the most effective way of learning it, you need to do more, right? So I don't know, have you guys ever seen the pyramid of your retention rate of different strategies? If you read something, you remember 10% of it. If you read it and write something, you remember 30% of it. If you read it, write it, and then teach somebody something about it, talk to somebody about it, tutor, that's why you actually are required to tutor for me, because it actually helps you in the end. You remember 90% of it. So I'm trying to get you to that top 9%, because if you remember 90% of it, you're going to raise that AP score to a 6. They're going to want to give you a 6 because you're so awesome, right? So that's trying to help you out, making sure that you're not just gypping yourself with a good education. So, and I take things very seriously in AP chemistry. Maybe AP other classes are not as serious, but I work my tail off for this class, and I have, and I will continue to do so. So I ask for a little bit more from you guys in response. So, in terms of vocabulary, what's the difference between kinetic energy and potential energy? Who feels confident they can look at their paper and kind of give me some feedback? Go for it, AJ.
Kinetic energy is the energy in motion. Potential energy is energy virtue or position.
Okay, so potential energy is more about positional relationships. And in chemistry, motion. In chemistry, we're not talking about this pen is higher than the desk and I drop it because it has potential energy. What does that do? That's physics, right? We're not talking about pens dropping. We're talking about chemical reagents and close proximity to others. Because there's this Coulombic attraction. Do you guys see that word, Coulombic attraction? I think it's Coulombic. Do you see that word? All right, Coulombic attraction. Me just taking some annotated notes on my notes here. This is the energy of attraction between a positive and negatively charged object, or the energy of repulsion from two similarly charged objects. So if I have an atom and it has like, electron cloud around it and it has a positive nucleus, and I have another atom, let's make it smaller, it's got an electron cloud. As it goes closer, or as it closes the internuclear distance between them, this negatively charged cloud and this negatively charged cloud will actually start to repel each other, right? That's a lot of potential energy too, because there's an energy of repulsion. But this nucleus starts to attract to this electron cloud, which is an opposite set of energy of attraction. There has to be this nice balance between them, because if they get too close, the nuclei overlay each other, and what starts to happen? Repel or attract. If nuclei overlay each other, they repel. It's like nucleus on nucleus, positive on positive. They repel. And then the electron clouds are on top of each other, and then they repel. So there has this Goldilocks region, this happy medium of where they position themselves so they're in the best energy instance, or the best energy situation. So what we saw on the reading, and I'm going to kind of show you that from here, we saw this graph of potential energy, and we saw it kind of had like this dip right here. It's on the very first page. Did you see that? Okay, this was when the atoms were very far apart, and so this is atom 1 and atom 2, and when they're very far apart, they have their own kind of inherent instabilities, and so they have a lot of energy about them because they're unstable. Their potential energy is high. When they're over here, I'm actually going to draw this high, like this. When they're over here, like they're smack dab on top of each other, there's a lot of that repulsion energy going on, so their potential energy is high. But when they're in that perfect, like atom 1 and atom 2, are their perfect internuclear distance from each other, I'm going to draw them touching, but that internuclear distance is the distance between the two nuclei when it's in the perfect balance of attraction and repulsion. It's actually a very low potential energy, and that's a really good thing. That's a really good thing for atoms, because if they're a low potential energy, that means they're very stable. Okay, so this is what we call bond length, the length of a bond. And so that length of the bond is where that Goldilocks region is, at that perfect balance of attraction and repulsion. This would be like the porridge is too hot, the porridge is too cold, and then like the perfect warm porridge of Goldilocks. Okay, so we do call that bond length. It is related to the potential energy. We want everything to have low potential energy because of that stability aspect. Yeah.
Why is there more energy when they're farther apart?
Because separately, they maybe they don't have a particular set of electrons, like an octet situation. So themselves, they're very unstable because they're highly reactive, and they actually end up by themselves. They don't have any attractive or repulsion, right? Because they're by themselves. But whenever this gets close, so one gets closer to two, that attraction stabilizes it. So that was what the graph was. And then let's kind of recap a couple more ideas as we move on. So heat. Heat is not really a single thing. What would you define heat as? Look back at your vocabulary. Yeah, Jacob. So the transfer of thermal energy. But what is thermal energy? Okay, so we're going to talk about thermal energy in a second on notes. We'll talk about how it's an accumulation of potential energy, and it's like a lot of energies combined together. It's actually all the kinetic energy, whereas total internal energy is all the kinetic energy and all the potential energy together. Okay, state function. Let's kind of get away from definitions for a second. State function. That is a weird way to describe something in chemistry. But if we can't measure heat, and we can't really measure energy, the only thing we can measure is the change in heat or the change in energy. But we do that, of course, in a roundabout way of measuring temperature and some other things. So state function is what we call anything with a delta, like delta H, delta E, delta S, delta G. We're going to describe these all differently in the end. This is change in enthalpy, change in energy, change in entropy, change in Gibbs free energy, which is the last part of this unit. We're going to be really honing in on thermochemistry and then thermodynamics. So they're connected, but they're two different ideas. So that's why we're doing all chemistry first, because most of it's background information for you guys as well. So anything that's a state function is, we don't really care what happens in the middle. We just want to know the beginning, and we want to know the end, and we're going to measure the change from beginning to end. And you've seen graphs that relate to this state function idea. Oh, all my work for lead 2 iodide getting away here. So you've seen graphs that indicate something like that. You've seen a graph like this? Yes? Do you remember that this is like reactants, and then there's some activated complex, and these are products? So as a reaction occurs, there's a change in potential energy. Sometimes it's labeled potential energy, sometimes it's labeled energy. But over time, as a reaction occurs, energy is changed. Who cares what the heck happens in the middle? All this in the middle right here is a mystery sometimes. And it's actually our next unit called kinetics. It's like the mechanism of a reaction, so we're going to learn about this when we get to kinetics. But right now we're talking about, I start with this energy, I end with this energy. What happened to my energy over time? It went down. So what kind of reaction would you call that? If the energy of the reaction, if the energy of the chemicals in the reaction is lesser. Exothermic reaction, because it released energy to the surroundings, but the system itself, the system lost energy, so we do call that an exothermic reaction. So, did you care about what happened in the middle? No. We cared about the beginning and the end. The difference is called the state function, and we label it with a delta. Okay, E, Q, and W. What do each of these mean? E is energy, which is energy is equal to Q plus W. It's actually delta E, but same. We're going to get to those equations shortly. What's Q? Heat. And what's W? Work. And work is equal to negative P delta V. Okay, so we're going to talk about compression and expansion of gases and how that relates here shortly. Heat versus temperature, we're going to get to the definitions on that. There are two heat capacities, and you have been actually exposed to specific heat capacity. We label that with a variable called, oh, okay, I'll go through the units actually. Joules per grams degrees Celsius. Did you guys see Kelvin like at all at the beginning of this? We are totally out of Kelvin world. We are in Celsius world again. Okay, gases use Kelvin. Thermochemistry uses Celsius. Nobody uses Fahrenheit except for us, US. Okay. Okay, so C, this is little c, lowercase c. It doesn't matter if it's capital or lowercase. Be very evident or be very specific when you write that. That is specific heat capacity. Heat capacity is just big C, big capital C, and that's just joules per degree Celsius. The only difference is that there's no grams there. We're going to talk about the differences as we go. But I'm giving you some of this background information because maybe I mentioned this to you guys before. You have to see something 7 times to know it. 7 times. So if I say it once now, once in the middle of the lecture, and then you do it once for homework, that's 3 times in 24 hours. You got to do the rest though. You got to get the other 4 times. Okay, so we're going to talk about this being an extensive versus an intrinsic property. Okay, so in terms of background knowledge you have from honors come to now, we're in different places with different people, different situations. What equations did you see throughout that were familiar to you? Q equals MCAT. What else? Was there any other equation that was familiar? Heat capacity, like with this. So that C is embedded in there. Good. Anything else? How about Q is equal to Q? System versus surroundings, right. Q the system versus Q the surroundings. Q the system is equal to the Q the surroundings because law of conservation of energy, energy is neither created nor destroyed, energy is conserved. So if I got a cup of coffee, let me say this, let's call this ice cold. Ice cold here, okay? If this is my system, my water in my water bottle, and it's ice cold, and my hand is warmer, what's going to happen? Let's say this is like full of ice, just imagine it's full of ice. What's going to happen over time? Heat from what? My hand is going to go to the ice. Okay, where is the system? In the bottle, where's the surroundings? My hand, the air, the bottle, everything that's warmer than it will be transferring energy in within, and it will cause some changes. Okay, so we're going to talk about those changes. I'm going to try to hit the important points because some of it is repetitive from your reading, but of course, write down what you need to. I may or may not stop when you want me to. It's not that I don't love you. It's just that I have a lot to do with you today. Okay, so we talked really briefly about systems and surroundings, but before I even hit this, I'm going to kind of talk about something that might be confusing at first, but we're going to talk about it now, and we're going to kind of hit the calculations kind of later. If I have a phase change happening, you know things are changing. Particles are moving different speeds. Particles are moving faster. Generally, if particles are moving faster, what are we saying about its kinetic energy? It's relatively higher, right? But kinetic energy, the average kinetic energy is directly proportional to temperature. So then we would say also with that increase in kinetic energy will also be happening. the temperature would be increasing, and not always is that the case, but we're just going to pretend that's happening for now, okay? So most chemical reactions do have, I've lost the marker. Most chemical reactions do have a temperature change component with it, as do some phase changes. Phase changes are just going to be solid to liquid to gas or vice versa. So tell me really briefly, if I go from solid to liquid to gas, what's happening to my kinetic energy? It's increasing in kinetic energy, okay, due to the lesser attraction between the solids, the liquids, and the gases, because they're starting to spread out, and the potential energy is also changing. The potential energy of a solid, they're in really close proximity, right? This one's different, this one's different, it's getting bigger, bigger, bigger. So the potential energy does change as well. But we're going to hit that one, hit phase changes. I just wanted to let you know there are a lot of energy changes happening even during a phase change. And vice versa, gas to solid would be decreasing in kinetic energy. And so if you had to identify these with the words exothermic and endothermic processes, notice I said processes, not reactions. Reactions would be like the term used for chemical reactions, whereas this is just a process. As I'm going from gas to solid, would that be considered an exo or endothermic process? So we're going from a high energy state to a low energy state. Exothermic. That's the only way you can decrease energy is to release it, right? So what's your question?
Like, is volatility of certain like solid liquid or gas, is that like proportional to its potential energy? Like,
So it's proportional. So it's related to potential energy because it's related to the intermolecular forces. So if something's very volatile, it means that it has very low attraction for each other, right? So it just starts to evaporate. That's because its individual molecular potential energy is high. But if it's really well attracted to other things, its potential energy is a little lower because it's that happy Goldilocks region. They're attracted because of high intermolecular forces. Deep question, but I'm not ready for that just yet, okay? All right, so we see that process going from gas, high energy to low energy is exo. So then going from low energy to high energy is endothermic process. So we're going to relate these terms to actually enthalpy values, which will be like the enthalpy, which is delta H, is called enthalpy. Enthalpy of sublimation. So enthalpy of sublimation. What is sublimation? Going straight from what? That's deposition. Solid to gas, okay. If I'm going from solid to gas, would this enthalpy value be positive or negative? Positive because it's an endothermic process. And then vice versa, enthalpy of deposition, which is what you guys named off to begin with, which was what to what? Gas to solid, that would be an enthalpy value of negative because it's releasing energy back to the surroundings, so it becomes that solid once again. So these values would actually be the same exact value because we're talking about the same exact process, but they're opposites in nature. So what's opposite here? The signs, right? So the number, the quantity, the magnitude of the number is the same. All right, so we're going to hit that probably towards the end a little bit. But as we go through, remember that when we talk about the system, we're talking about the chemicals of interest. Not necessarily the glassware and the beakers and the room. That actually is all miscellaneous. That's considered surroundings. So chemicals of interest would be the system. That's the perspective we're really honing in on. And the surroundings is everything else, including the universe. We're going to talk about the universe a lot, as you know. Okay, so here's your definitions again. And as a quick comparison, you of course have your outline or your, if you printed out the sheet, you have the study guide itself. You can star those if you want to. These are the most important ones that I think are going to be relevant for our discussion today. So we're talking about energy. And energy, we talk a lot about, oh, we use up energy in our cars, and we use up energy in the electricity. But what is that energy doing? What is that energy doing in a car? Say again, Kurt?
Transferring to
Maybe. So, but what is? So we're taking our gas clean, right? We're combusting it. What is that combustion creating? Through all combustion is causing carbon to carbon dioxide and water. Okay, so carbon dioxide and water vapor in this case. That's a gas, right? So that gas is causing some pistons in your car to move. right? So that expansion, that spark causes the gases to expand, or gases to be created, which would expand, which would push the piston. We're causing movement because of that gas expansion. The pistons go, the axles move, the car goes, right? So that movement we're doing is we're moving our pistons a distance, which then transfers to travel, right? So we're talking about gas expansion, not really like a car moving the distance, but more the gases themselves. And power is also kind of the same thing as movement. How does the electricity work in this room? How are these things all turning on? Anybody? So, you guys know how electrons move through metals? They're conductive, right? They move. Okay. What pushes them to move? Not really attractive, because that's a long distance. Like if I'm getting power from Duke Energy and they're 25 miles down the road, like how is there a movement? Well, I'll give you the basics of it. The electrons are pushed along a way through a rotating magnetic force. And so the electrons move because they're negatively charged, right? And they move, and this magnetic force is pushing them as you go through, and the electrons moving a distance is what's causing the power because the circuit is connected. I'll bring in electrical engineer in here. We'll talk about that soon. But same thing, power is working, or power that we talk about in natural and like the everyday sense is not really power in the physics and chemistry sense, but it is movement of electrons. So make sure that you know the difference between these kinetic energy, potential energy. Temperature, which we did talk about last unit, is the average kinetic energy. It's directly related to temperature. I'm trying to draw a fish here, okay? Directly related to temperature. That is something we already knew. And that heat, this is the new one. Heat is the sum of all kinetic energy. And that is not a standalone temperature. Heat always, usually it's a transfer, so it's a change. But we're talking about the sum of kinetic energy is transferred. And that energy unit is going to be joules, whereas temperature is energy unit. It's going to be actually degrees Celsius here. And joules is how we're going to express energy in general as well. So total energy, which is E in this case, we can call it E or delta E. We're going to call that measured in joules because it's related to kinetic energy and how we can relate kinetic energy to heat. So in this case, total energy is very hard to actually find itself because this potential energy here is pretty difficult to measure. So if you're difficult to measure and you're a part of a whole, it's really, if you can find the kinetic energy, that's fine, but if you can't find the potential energy, it's going to be relatively difficult to calculate the internal energy. So we can't really calculate that directly. We calculate it indirectly through the measurement of Q and work. So what we're going to find later, I think it's on the next slide, it might be 2 slides away, is that energy, internal energy of a compound or of a system is equal to heat plus work. Because we can measure these two in an indirect way, but we can't measure potential energy, so we can't do it just kinetic energy plus potential energy. So that's some of your background information. What about this? Is this background for some of you guys? Let me see which one you do this one. Is this background for some of you guys? Okay, let me see where we are then if I ask you a couple questions related to that. So if you see this diagram on the left, you've seen one like this before. What about the one on the right? That's the new one. That's the one I don't think mainly anybody has seen. But if you're looking at this one, can you tell if it's an endothermic or exothermic reaction? Definitely exothermic. The reactants have lost energy. They've given up energy to form these products. So that loss of energy is definitely exothermic. But how much? You see this right here? That is the exact amount of change from where the reactants began to where the products ended. We call this delta H. That is our enthalpy of change of the reaction. So enthalpy of change is enthalpy of reaction. And that has a specific quantity. Is that going to be a positive or negative value? Negative because it is exothermic nature. Okay, so over here, it's actually supposed to be resembling kind of the same reaction. But in this case, the reactants are where the arrows start, and the products are where the arrows end. Bless you. So the products, the reactants in this case are H2 plus half an oxygen. You can see that these are reacting to form water, but it's giving you two reactions at the same time. H2 and O2 yield water liquid, which is hard to see, but that's an L there. Or H2 and O2 yield water gas. Well, this bigger drop in energy to negative 286 kilojoules is the biggest change of energy from the gaseous state to the liquid state, because the liquid state is of different energy than the gaseous state of water. So there's a bigger drop in energy because liquids have lesser energy than gases. You got me here? Did you see that difference? Simply because it's a liquid versus a gas. So, but if I tell you the difference in energy of gaseous water and liquid water is negative 44 kilojoules, then you should be able to tell me the delta H associated with this one. Say again. Negative 242, so you take 286, subtract your 44, the difference is that. So you could look at a graph, you could determine the enthalpy of change based on some other values given to you possibly. Like I could give you values for this one, and we can actually find this as well. So it's graphical analysis using delta H as change. Okay, so in this case, I know it's exothermic, but it's energy absorbed or released? Released, so making sure you can describe it in 3 different ways. All right, and this one is endothermic. We have potential energy of reactants low, potential energy of products high. How did they get high? They absorbed energy from the surroundings. So using that vocabulary is pretty important in terms of finding where our gaps are. All right, so this again I think is mostly review, but in terms of talking about reactions, we're going to try to correlate exothermic with a negative sign in terms of the perspective of the system, and endothermic is a positive in reference to the system. The system is getting energy. So we're talking about that change in reference to the system. Now, this is the new part. This is the work part that no one has talked about yet. So if we're talking about work and chemistry, we're talking about the ability to move a distance, but that distance is generally in terms of gases. That's the one thing that really moves in chemistry. It's not biology. It's not physics. So we have to talk about how do we reference that in terms of a system. Well, if this is my system in here, and I do work on my system, I'm taking work or energy from the surroundings, the outside, and I'm doing work on my system. Well, the way that looks to us visually is a compression. We're taking the outside, the surroundings, whatever's happening, this is probably a piston in this case, like an engine, and we're doing work on the system, so energy is flowing into the system through a compression of a gas. Okay? Oh, I drew that for this is supposed to be for this one, but I'll switch that real fast. I thought I was doing work on the system first. All right, this is compression. And then that's in reference to the system. We're doing work on the system. So this compression is making the volume smaller, and we call that positive work because the work is being done on the system. Vice versa, if the work is being done on the surroundings, the system itself is losing energy. It's losing some sort of kinetic energy or potential energy, something about it. So it's going to be, what's the word for this? It's getting bigger. Expanding, right? And so if it's expanding, the volume is going to increase. And so it's pushing on the walls of itself, right? It's pushing on the piston. So itself is losing energy, which we have a negative sign. So W is work. Q is heat, which I didn't write up here. But if the sign is positive Q, that's an endothermic reaction. And if the sign is negative Q, then it's an exothermic reaction. All right, so these are going to be things that we're using variables-wise in an equation. I think on the next slide here. Question?
Hyphens before the W?
No, that's just like a bullet.
Oh, okay.
Yeah, that's not a negative W. Thanks. Yeah, because that's pretty important to know if it's a negative or not. Can I go forward? Yes? Okay. Some of you guys are just watching and listening, so you guys are taking notes. I just want to make sure I'm trying to hit all you guys what you need. So here's the lovely equation we've been speaking of, but we haven't used yet. Energy is equal to Q plus W. So the internal energy change of a system, which is very difficult to measure because of its inclusion of potential energy. Potential energy itself is hard to measure. So we're measuring the energy change of a system by referencing Q and W. This is only really 2 forms of energy we can actually calculate. So, like I said earlier with the state function definition, I'll just clarify this. when I say it's independent of the pathway taken or the mechanism taken, that's what we were talking about here. State function is just change from beginning to end, ignoring the method of mechanism or the method of the pathway it took to get there. So since heat and Q are not state functions, meaning you don't see a delta, right? You don't see like delta Q and delta W. Those are actually measurable, or you can actually calculate them. So that's why we're able to do this calculation in this fashion. So to prove to you, this is kind of like a little proof, how work is related to chemistry, we are referencing that volume change quite a bit. Well, truly, in physics, work is equal to force times distance. Who's taking physics? 2 people. You remember this? Work is equal to force times distance. Okay, well, I will enlighten you, that is the fact. So, if work is equal to force times distance, how does that relate to us? We don't have things really moving at distance necessarily. So, pressure, so if you're talking about just P, pressure in general, pressure is the force on an area. Force over area, so force per area. So if I have a balloon and I put a lot of pressure on its entire surface area, it may or may not pop, right? A lot of force on its entire surface area. But I take one pencil and I put a lot of pressure on one part of the balloon, it's going to pop because the pressure has increased because it's a smaller surface area versus the entire surface area. So we're going to rearrange this. Can you guys go ahead and solve for F for me? F is equal to P times A. Okay, plug that in here. Work is equal to P times A, so pressure times area times distance. Okay, so if I have area of like a cylinder, volume of a cylinder, and I kind of have a picture right here versus me trying to hold it in my hand, and if I have this area right here, like this surface area, and this piston moves the whole area, that whole like whatever the pi r squared is, and it moves down a distance, that now is called just a volume, right? Because height, this is basically height times pi r squared. Isn't that volume of a cylinder? Impressing is my geometry, whatever this is, geometry? Okay. So this right here is now volume change in terms of chemistry. So area and distance collect together to form volume. So pressure times volume is equal to work. But it's not just the volume, it's the change in volume, right? It's the distance that moved. So that's why it's delta V, which is what this is. Now, since we're talking about we're talking about work in reference to the system, if the system is causing change, the system making the volume get bigger or the volume get smaller will cause the work to be positive or negative based on what's happening. So we put a negative here to correct for the fact that we're talking about in reference to the system. To the system. Yeah. We will not talk about the height. We will talk about the volume.
But like, how do you measure the volume?
You measure it in whatever you can do. Whatever you do needs to be the same for the radius and for the height.
I was just thinking, like, because it's a cylinder, like, weight times height.
That's of a rectangular prism, though.
Oh, yeah.
Yeah. Geometry. I remember this from what, 9th grade when you guys take geometry. Okay, so let's talk about work now. And let me actually tell you one more thing. What unit will this work be in when I calculate this? Likely. What's my pressure unit likely? Pressure. Pressure of a gas. Thank you. Generally the atmospheres, and volume will generally be, say again? Liters. Okay. Atmosphere liters equals work? What the heck is that, right? That doesn't make sense. That work is in the units of pressure in liters. Atmospheres and liters. There's actually a correction factor for that. 1 atmosphere liter, and write this down because I'm not even sure. I think it might say it in your reading once. 1 atmosphere liter is equal to 101.3 joules. Yes? Okay. That number looks familiar, right? Pressure. So there's that like kPa, kilopascals, is that correction factor, but it correlates it to joules, which is what work should be described in terms of its units. Yeah. Are kilopascals joules per liter? No. I don't know what kilopascals are related to. I think kilopascals can be converted in a way to joules. That's why atmosphere liters is equal to joules. trust me on this one for now. I'll see if I can find the proof of it later. Okay, so in terms of calculating, let's do a calculation first, and then I'll come back to this. All right, let's do this one. Let's just go straight to the example problem. Okay, so identify the givens as we go. Ready? What are my givens? What's my question? Okay, so what is this though? What variable is that? Delta E. I'm looking for delta E. Okay, what else is given? Okay, but is that a positive or negative process? Positive endothermic process in which 15.6 kilojoules of heat flows. Okay, so stop there. Q is equal to positive 15.6 kilojoules. Okay, so that direction is very important, positive. Where 1.4 kilojoules of heat of work is done on the system. What kind of work is that? Is that positive work or negative work? It's done on the system, right? The energy is getting work, right? So work is positive. It's being done on the system, 1.4 kilojoules. Okay, this math is uber easy, right? So then what do? Energy is equal to Q plus W. So positive 15.6 plus 1.4 kilojoules is equal to? If you write 17, it would be incorrect. 17 what? 17.0 kilojoules. Sig figs. Decimals and sig figs, I'm sorry, when you're adding numbers, sig figs are in the decimals. So the least number of decimals wins. The least one is both 1 here. So the delta E, the change in energy of this process was 17.0 kilojoules. Not bad, right? Let's do another one, similar. I'll let you do that. Levi, get me started. Alright, so we describe is that Q? Describe the variable it's describing as well. Just because we can write in our givens.
Okay, well,
So Q is equal to?
no, you're finding internal energy.
Okay, so that's my question. What's my given for Q?
Negative.
So it's released, so negative 125 kilojoules. What's my given for W?
Positive.
So it's saying has work done on it, so positive 104. Okay, and then what do? Okay, so delta E is equal to negative 125 kilojoules plus 104 kilojoules. What's that answer? Negative 20. Did I put? Oh, okay, I did. That's at 5. Negative 21 kilojoules. So please make sure you're showing your work for me. If it's defining givens, lovely. I absolutely agree this is the best way to always start a problem, even if it's stupid simple like this. And then plug in your variables as is. Now, this one. And this is going to lead me into key information. Let's write down all of our givens first. And you can write on your paper. Okay? So every bit of that information is important because now we have a situation where heat is not just simply given to us as heat. You see that? We have all the variables to calculate heat, which this is background information. We just went over as a warm-up, and I'm going to hit it a little harder on the next couple slides. But what would you have to do to calculate heat yourself in this instance? You would have to do Q equals impact. Give me a thumbs up if that makes sense. Yeah.
Okay, so 2480 joules per Celsius mole, but you have to like take it for.
So the easiest, the lesser of two equals would actually take your grams to moles. See our helium? So this is actually, so generally specific heat capacity has grams in it. This is molar heat capacity, so it has moles in it. It's the same story, it's just a different unit. But in this case, we could take our grams easier to moles. Yeah. It's not actually an A. We say MCAT just like dirt over P. There's no I, but it's Q. And this is what. Let me, before I hit this all the way, I thought I had this in the right order that I wanted to, but I wanted to give you guys a break from me in between these two big topics. But do write this first equation down first, and I'll teach you this as I do this problem. That way I'm not doing this all at once. Seriously, this is like the equation of the day. Q is MCAT, and let's define each of these. Q's units, because I know you guys love units. Make sure you're with me here. What are my units for Q? They have to be in joules, right? Joules or kilojoules, but joules is probably the one to go, that you'll go with most of the time. M has to be in grams, right, because this is mass. This is going to be defined in grams, most likely, assuming that our specific heat capacity is in grams in this case. But most of the time it will be, it's just that first problem is not. C is specific heat capacity, and that's units are joules per grams degree C, or C's grams. And now delta T is change in temperature, and we always do temperature change and volume change and whatever change as final minus initial. Okay, you have to do T final minus T initial. Just like on my referencing the givens on the previous problem, I did volume initial and volume final because you have to do changes as final minus initial. And you do this in physics all the time if you take physics in college. So this is going to be in degrees Celsius. Okay, so this is MCAT, and then later on we're going to learn that Q can also equal just cat, C delta T, with coffee cup calorimeters. All right, so let's go back and finish this problem now. Okay, so let's calculate Q first, since that's part of the question. Calculate Q. So Q equals MC delta T. What do I want to do first? Let's get the grams to moles, because in this case the M will be moles because of this weird mole thing that's happened with my C. So Q is equal to 313 grams of helium, molar mass of helium. Look at me showing my units, my conversion. And if I am modeling this for you, it's not just because I want this to look pretty on my paper, it's because I want you to do the same. I have to tell my honors chem this. They're like, well, you did on the board. I'm like, yeah, if I did on the board that way, you should be doing it that way too. Like, I'm not just doing it my way and you're doing it your way. Like, we should have the same way. Okay? And then, what's my C value? 20. Did you say the joules? I didn't hear you. Oh, okay. 20.8 joules per mole degree C. And what's my delta T here? Oh, I didn't write it down. What was it? Oh yeah, it decreased 15 degrees Celsius. So what does that mean? So the final is lower than the beginning, right? So when you do final minus initial, it should still be negative. So it should be negative, right? So if, let's say it dropped to negative 15, negative 15 minus 0 is negative. Just make sure you're putting your sign there. Okay, so what's Q then? You guys have a calculator? Because I can calculate on this. Can somebody calculate that real fast? So I'm not running through my mind. Oh, there it is. I got it. Negative. Wait on you. 24414 joules. All right, before we move on, can we go ahead and convert this? Can we go ahead and convert this to kilojoules for me? Negative 24.414 kilojoules. Just in case, because sometimes it's expressed. It doesn't say it, but it might be expressed in kilojoules. Okay, so we got our joules. What do you want to do next? I mean, we got our heat. What do you want to do next? We're going to wait on you to tell me. Find where negative P delta V. Work is equal to negative P delta V. What is my pressure? 1 atmosphere, and it says it stays constant, so that's negative 1 atmosphere. What's my delta V? So how are you doing this? Okay, so 1840 liters minus 1910 liters. So you're doing V final minus V initial. And calculate negative, oh sorry, no, negative times a negative, right? Positive 70.0, oh no, 70, not 0.0 atmospheres. I work this all. Okay, so this is work. Okay, so atmospheres and then kilojoules, right? I mean, that's atmosphere liters, by the way. Atmosphere liters. Say again? But they're not the same. But which one? The atmosphere liter one, right? Okay, so the 70 atmosphere liters times, what was the conversion? But who gets this, the top or the bottom of that? 101.3 joules is equal to 1 atmosphere liter. That's our conversion, right? Say again? Yes, but people couldn't remember if 101.3 went joules or if it went with atmosphere liters. So memorize it goes with joules. Atmosphere liters cancel, so that's 7,092.75 joules. And you're like, okay, I got joules. And I could take this to kilojoules, or I could just add this to my original joules that I have here. Yes, yes? So add those together. So delta E is equal to Q plus W. So Q was negative 24414 joules. Add that to 70.75 joules. And what do you guys get? Did you put your negative on there? Yeah. This is a negative, and this is a positive. So just basically do 7,092.75 minus that big 24,000 number. What? All right, negative 17,323 joules. Round that to a correct sig fig here. Correct sig figs. Vinky, how many sig figs should I have? 3. 1, 2, 3, 1, 2, 3. I'll go. This really only has 2, right? But this converted would have 1 decimal. I'll go with 3. Negative 17.3 kilojoules. Because if we have a very large number like this, it's a lot of numbers to write, so generally do convert to kilojoules. Okay, I'm going to pause for a moment and reflect on what the heck does this mean? What does this number mean? Okay, yeah, it's defining delta, but what does that mean? The total change in energy of the system decreased by 17 kilojoules. During this balloon, you don't even remember the question was the balloon changing in volume, changing in temperature, and you're like, okay, I know all that, but basically as this whole system is occurring, or as this whole situation is occurring, it's dropping in energy by 17 kilojoules. Woo! That's what it means. All right, give me a moment of your time then. Let's go ahead and do a practice set of these so that I don't move on too quickly. I have 11 questions. 1, 2, 3, 4. There are 5 that are starred. You're going to start with the stars. I'll let you guys do that, but I've been saying that this whole time. You guys haven't come and grab your packet. This is not everything for this unit. I will copy the problem set so far, not the lab. And then we'll move on to the expert in a minute. So I'm going to give you guys 10 minutes to practice on that now. 10 minutes to practice now. I lied, there's six. There's six, not five. And let's make an agreement with each other. Let's go ahead and just claim that this is going to happen. You will write on a separate sheet of paper for this problem set, because ain't nobody got time to be squeezing some words between those lines. And you will use your units. We will label this. When I take it up, I know what I'm looking at. Okay? So please have a separate sheet of paper for these problem sets, and just continue them all on the same. That's right.
What is what?
Which doesn't make sense because
I'm not working on into system or out of system. Alvin, I told you to find the proof. 1 joule is equal to a Pascal meter cube. So 1 joule is equal to a Pascal meter cube. That's why that conversion works. What's liter cube? No, it's liter. Never mind, that's wrong. I break this candy bar into 16 pieces? Do you guys want a piece?
Yes.
That was a stupid question. At your leisure, you can grab a piece. I'm not going to cuss you. Just one piece. Just one piece. Are there 16 of us? There's 17 of us. Oh, that's right. Okay. You were so quick to say.
We got 4 pockets.
There's one for everybody. Somebody dropped at my door, and I don't really need a whole bar of chocolate, so. Alright, finish that last one you're on, and then come back to me. We're doing heat, heat, heat. Huh?
What does a joule equal?
In terms of it equals a kilogram meters squared per second squared.
Also on the ATP, there's a
Does anyone want another one?
Alright, come back to me at the front. We're gonna do heat now. I'll give you like 30 seconds, and then we have a little bit more to do today. We get out at 10:30. Okay, stop your conversations. I know you're in the like you're knee deep in this problem set, but that is one that you'll finish for homework. There's 6 questions. You probably got through 3 or 4 at least. So, in terms of heat, since you're also going to be doing some heat homework, I need to give you some good quality instruction on that first. So, back with me. This is information you should know. Please write down this conversion. I'll review it as we go through. But the conversion of 1 calorie, and that's an intentional little c calories. Little c. 1 calorie is equal to 4.18 or 4.184, as you might see me describe it sometimes. Just because like my own things are drilled in my brain, and I can't lose these like last numbers my chemistry teacher taught me. But that's equal to 4.18 joules. So if we ever have to convert between calories and joules, they're both forms of energy. But you can convert between the two with that conversion. And so if you're looking at the back of a package of cereal, right? Who ate, give me something you ate for breakfast. Count chocolate. Okay, count chocolate is probably like 120 calories per 100 calories per cup. Okay, so 100 calories per cup. So that's good. Is that big C calorie or little c calorie? It's actually big C calorie. The nutrition labels, and this is like a fact that they don't think the layman person can understand, is nutrition labels put everything in. They write them in little c calories, but it's truly a big C calorie. So that cup of cereal has this conversion. You can do this here for me before I move on. Has 100 calories in it, which is actually 1 big C calorie is equal to 1,000 little c calories, right? So 1 big calorie is equal to 1,000 little c calories. 100,000 calories in that 1 cup of cereal. If the layman saw this, right? With skim milk on top of that, it's probably what, another 50-something calories or something. Anyway, if they put this on the back of nutrition labels, people would freak out. They wouldn't understand what it means because our body uses little c calories, which is a form of biological energy. But that doesn't make sense to the normal person, so they're like, let's keep it easy for these people and put 100 calories in the package. Isn't that kind of crazy? They don't trust us, basically. All right, so let's go ahead. Huh? I don't know. It's because the kilocal, it's because we don't use metric units, so if you put kcal in there on our packaging, you're like, what the heck's a kcal? But it's a kilocal. It's 1,000 calories. Because instead of using that, they use a capital C. It's because they don't trust that we know what a K means. We're the Americans who don't use metric. All right, take a minute to absorb what I just told you, and then I need you to talk about heat loss. But it's big C calories that you're talking about. It's not little C. Yeah, you do need 2 million a day. Yes. All right. Side conversations halt. Shh. Back to me, because I'm going to hit the highlights and then we'll do examples. I'll save some of the other information that's helpful to fill in the gaps in between. I'll do that tomorrow with you. So we already went over internal heat. If I'm doing internal heat calculations, that's just like, shh, guys, hush. If you're doing heat calculations of just a simple compound and itself is changing its own temperature, or it's warming up, like for example, you put a piece of metal on a hot plate. It's not reacting with the surroundings, it's not reacting with anything else. Itself is changing temperature, so you talk about its internal energy change, and that's just Q equals MCAT. But if I do have a system and surrounding where I have like water, and then let's say a piece of hot metal that I drop into it, or your hand in a coffee mug or something, we have to talk about heat transfer between 2 objects or between 2 different systems. So we do have to label one the system and one the surroundings. Remember, the system is always the one that we're talking about in terms of the chemicals, whereas the surroundings is everything else. So we have to set up an equation where Q system equals Q surroundings. But if Q equals MCAT, then what we can say is, let me give myself some space, Q system equals Q surroundings. So then that means MCAT of the system equals MCAT of the surroundings, right? So how many variables do we have here? Okay, we're going to have 6 variables in our system. That means that you need to specifically organize your givens and information, and am I referring to the system or am I referring to the surroundings? Make sure you have that crystal clear. If not, you'll blend your masses with the wrong system or surrounding. Now, I can't have both system and surrounding gaining energy, right? As one gains, it's because the other one's losing it, yes? And that's due to the law of TD. What am I talking about there? The first law of thermodynamics, energy is conserved. It's neither lost or gained. So by the universe as a whole, but individually, a system can lose energy and a surrounding would gain it, or vice versa. Just make sure you put your sign on the appropriate side as we do questions like this. So this is actually called calorimetry. And so calorimetry means that we're going to use a calorimeter. That sounds really similar to colorimeter. The colorimeter is used in your Beers Law lab that measure absorbance. That was colorimeter. This is a calorimeter. Calorie, right? Calorie. Got it? This is heat. Please don't use those words interchangeably. They are not the same thing. Totally different systems. I'll show you what a calorimeter looks like now. Can I go forward? Okay, let me show you what that calorimeter looks like. Right here. Oh, here it is. Look at this fancy dancy styrofoam cup system we have here. This is a coffee cup calorimeter. And this is what we use in Honors Chem. This is what we use because styrofoam is the absolute best, what? Insulator. It does a really, really good job of keeping stuff inside, like that heat that we want to stay inside so we can measure the temperature changes by shoving a thermometer in the lid of it. So if everything stays in there, we have a contained system, right? Now, these are actually the ones that most high schools use across the nation, AP chemistry classes too, because we can't afford these. These are bomb calorimeters. Bomb calorimeters are what they use in like nutrition labs or like at Duke Energy. They have their coal, and they have to. I saw this in action. It's kind of cool. They have their coal, and they put it in here, and then they surround it with oxygen, and they basically combust their coal to see their energy output of their piece of coal to see how rich it is in energy, basically, right? So they combust it in this container, but in the container is water as well. The water can actually capture the energy by heat transfer, and they measure the temperature change. As they measure the temperature change, they can backtrack that delta T to Q. So they can measure their Q of their coal, yes? Now that is like really, it's a contained, huge, big steel drum, and it's at a constant volume, where ours is not really at a constant volume, like there's little gaps in air, right? They can escape. So that's why it's under, this is supposed to be under constant pressure because it's under our atmospheric pressure. Is this under constant pressure if I got some combustion going on in here? No, it's like gases are making lots and lots of pressure, so it's not constant P. So those are two different systems. It's just a calorimeter is just a device that we use to measure temperature change. We use coffee cups, real people use bomb calorimeters. Okay? And they actually do this with food too. If they want to figure out how many calories in a Dorito, they put the Dorito in there, they catch it on fire, they measure the temperature change, they backtrack temperature change to Q, and then Q to calories. Huh? Because it's just chemical energy. It's all it is. Doesn't matter where you burn it, it's chemical energy. That's how they figure out what to put on the nutrition labels. Okay. I will get some Doritos and we will catch them on fire. However, we have to do it under an open system, so it won't be very accurate. Percent error is going to be like 2,000. That'll be all right. So it's because energy is so hard to contain. Energy is hard to contain. All right, actually, before I do that, let's do an example with this one. Yes, let's do this one. Okay, so in terms of deciding on which equation to use, with me, please do not distract your peers. You're going to have to separate all the desks out again. Thank you. Because if you know it, doesn't mean that somebody else knows it, so don't be rude. All right, so if we have to identify which equation to use, either Q equals MCAT or Q equals Q, you need to look at all your givens first. So let's write down our givens. Required. Write down your givens with me so we can have an example question for later. What's the first thing you see? All right, so first thing I see is a question, actually. So question is C, right? What is the specific heat, capacity, but specific heat, of a metal, and this is, I'm going to label this whole column over here metal, okay? So that's my question. My mass of my metal is what? 50 grams. And what else do I know? It raises what?
100 milliliters of water.
Okay, so we're going from metal to water now, right? So now we have identified that there's two things going on. We have a system and we have a surrounding. The system is likely the metal. The surroundings is water. Water's mass is 100 milliliters, which is 100 grams, right? Density of water is 1. Okay, keep going.
Change in temperature of the water is.
Well, what's my final? Final is 36. And my initial is 34. So T final minus T initial gives me 2 degrees C.
And then what's my metal's initial temperature? 95, okay. And my final temperature of my metal is 36, because they always come to something called thermal equilibrium, which means that they end at the same temperature. Thermal equilibrium means they end at the same temperature, which happens to be 36 in this case. So 36 degrees Celsius minus 95, yeah. And so what is that? Negative 59 degrees Celsius, okay? So what are we missing here? What variable are we missing? Not the question, obviously, but what variable are we missing that we need? Actually, you're right, we're missing Q, but we can calculate Q if we really want to. What else are we missing?
Oh, I'm not sure. I know how to do the problems.
Well, I'm still waiting on what other variable we're missing. C of water. Do we actually don't know this? This is 4.18 joules per gram degree C, right? This is a given that you need to memorize. I don't think you'll be given it any other time. It was previously in my notes. I'm sorry I skipped it because I wanted to go to a problem first. So, because if you ask, have you guys ever seen the survey they do out in the public? They'll go to like New York Square, the city, and they'll do, okay guys, what's a calorie? And I'll ask the layman person. They're like, it's some kind of food. But really, a calorie is the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. Okay? 1 calorie, which is equal to 4.18 joules, right? This is equal to 1 calorie per gram degree Celsius, because it's the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. That is the definition of a calorie. And so if you ask a layman person, they go, it's something kind of food, but they don't know what it means. The amount of energy it takes to raise 1 gram of water by 1 degree Celsius. But that's the same thing as 4.84 joules. Question?
Will they always be in water?
Yes, most of the time. So water, you'll use it a lot. All right, but now that we see all of our variables, we see 2 MCATs, right? 2 MCATs. So that's the same thing as us saying system and surroundings. Let's call this one the system. Let's call this one the surroundings, because water is the surrounding. Who's losing energy? Why is the metal losing energy? How do you know? Its temperature has a negative sign, right? It's dropping. So this is going to have a negative Q, whereas this is going to have a positive Q because the water is gaining that energy. So how do we set up that comparison? We do Q of system, which I'm actually going to put M for metal. Q of metal is equal to Q of water, where Q of metal is negative and Q of water is positive. So this is that Q equals Q calorimetry heat transfer calculation. We're going to plug in MCAT for water, metal, MCAT for water, and solve. But instead of plugging numbers in right now, I hate to plug in numbers really early because then I end up writing something wrong and messing up a decimal or something. So I always use variables first and then plug numbers at the very end. So in this case, I'm going to scroll down because I just need some more space. So MCAT for metal is equal to MCAT for water. What am I solving for? What's my question? Oops, that's a negative actually. The C for the metal, right? Okay, so I need to isolate this C of metal. So I need to divide by what? It's the mass and the change in temperature. So I'm dividing by MAT. Okay, dividing by MAT, or M delta T of metal on both sides. That cancels the negative, that cancels the M, that cancels the T, so just C of metal is left. Yes? C of metal is left, and I can plug all this information in. Now is when I want to plug in. So can you guys tell me the data? Mine's way up here. So what's the data for mass of water? 100 grams. And C of water? 4.18 joules per gram degree C. Don't get lazy. These units are killer. Worse than gases. Keep going. What's my delta T for water? 2 degrees Celsius. And that's all for water. That was a positive value for the heat transfer. What's my, and that negative sticks with me. What's my mass of metal? 50 grams. And my temperature change? Negative 59 degrees Celsius. Let's simplify. What can we first simplify? The gram. Okay, so let's cancel the grams. What else? Degrees Celsius. What units are left? Joules per gram degree Celsius. Isn't that what the units of C is? Okay, so that so far makes sense. Joules per gram degree Celsius, what's remaining. But also this negative, right? Negative times negative is a positive. So in your calculator, whatever you do, please put parentheses if it requires it in terms of keeping your numerator and your denominator separate. 100 divided by 50 is 2. 2 divided by 2 is 1. 4.18 divided by 60-ish. That's what I was going to say. What's the answer? Something like that? Okay. Anybody else confirm? Approximately?
I don't know. I got lost somewhere.
It's okay. I was gonna say yes because it's a decimal. Most of the time, our C values for metals are really, really low. So I was expecting something low. What's the low number there? Anybody else confirm? 0.2 what?
0.283.
I thought you.
That's what I got, but that's not what I said when you were asking me what 4.18 divided by.
Oh, my bad. My bad. Sorry. Yeah, I was looking for this.
Yeah.
Sorry, because that's times 2. But anyway, so in terms of specific heat numbers for metals, you should expect low numbers. Metals. Give me your thoughts on this. Are metals? Can they retain their heat well or not well?
No.
Why do you say not well? It's easy to heat them and cool them. You have a pot of spaghetti, right? You heat it up, it's like boiling in no time. You take the spaghetti off, you put it on the stove for 5 minutes, it starts to cool down pretty quickly, right? Okay, but the ocean, if you went to the ocean now, it's November, right? Went to the ocean, would it be okay? Would it be still warm? Yeah, heck yeah, it would be. Because the weather outside is inherently hot. But water is a great way to retain heat, or it has a really high heat capacity. 4 joules per gram degree C is a lot. Whereas 0.2, basically, I want you guys to explain this in one sentence, and I'll give you a sample first. It takes 0.28 joules, very little energy, to increase 1 gram of metal by 1 degree Celsius. It takes 0.28 joules to increase 1 gram by 1 degree Celsius. But water, it takes 4 joules to increase 1 gram by 1 degree Celsius. That's a lot more. So water's has a high capacity, so it has a great way to retain energy, whereas metals really don't. Question?
Could you just put the problem if you said MCAT was negative MCAT and then solve?
That is what I did, but I think you guys were over there talking. So I said MCAT equals MCAT, and then I divided by my M's and my C, and I solved for the C. Okay, so I expect when I want work, the data chart is, I think, very, very helpful. If you don't write the data chart and you get it wrong, it's on you. I have no pity for you. But if you write the data chart and you plug in numbers and then I see, oh, there was a mistake there, I can give you partial credit because I can see where your transfer error occurred. But if you go right to plug, I can't give you partial credit much because it's just, I can't see it. Okay, so make sure you're protecting yourself from errors. Let's go back to specific heat now. Okay, so question, instead of asking this a quiz question, I'm asking it here. For number 1, select the ants that will equate for heat capacity. 1, 2, 3, or 4? 4. Okay, I just want to make sure. This does say heat capacity. This is different than specific heat capacity. That one is joules per degree Celsius. But specific heat capacity, little c, I'm going to explain what heat capacity is in a second. Little c, which of these could apply? Okay, that's one of them. Or 7, or technically 8, and I heard one more. 4. Sorry, this is really coming up. So, specific heat capacity, again, the definition is energy it takes to raise a mass by some temperature. So this is energy it takes. BTUs are British thermal units. These are all forms of energy it takes to raise a certain mass, pound, mole, right, by a certain temperature, Celsius, Fahrenheit, and Kelvin. These are all different forms of specific heat capacity because they all follow that same template. Got me? But the one we'll use likely is this one. Okay? All right, so last thing probably for the day, I got about 10 minutes left. One more thing. Okay, yeah. So in terms of defining different capacities, we have to talk about the capacity of the system itself, which is like the piece of metal in our last example. That is inherent
it says that's an inherent quantity that's associated with the properties of that metal. So different metals have different heat capacities. Like water, for example, has a really weird high one, but most other metals are like 0.2, 0.3, 0.4, 0.5. So they're very low, but it's an inherent property, which I think I had, maybe some next slide, it talks about an intrinsic property. But then we have like the container itself, right? The coffee cup calorimeter. It's an insulator, right? Does it absorb heat? Not well, but does it? It still does just teeny bit. So we have to account for that because let's say I have a thermometer sitting in my coffee cup calorimeter and it's measuring the heat exchange and it's like, oh, it went up by 10 degrees Celsius. But there's a little teeny bit of energy that's transferred to the container. Did I account for all the temperature change? Did I really account for all the heat change? No, because some of the heat went to the container, not to the thermometer. So then how do we account for that? Well, we have to have these standards of heat capacity, which are associated with the container. Like styrofoam, we'll actually get our own heat capacity based on the exchange of energy that should have occurred, but then actually occurred. So like theoretical and experimental. So this is going to be an extensive property that relates to like how much you have. So it does depend on the amount of like the size of your containers. Like a big coffee cup calorimeter versus a small one, they'll have different C values, and this is a capital C. Did you read a little bit about this? Heat capacity versus specific heat capacity? Okay, so in terms of talking about the energy absorbed, we will call that heat capacity capital C, and to quantify the heat exchange that wasn't accounted for with the thermometer, we will calculate that by doing Q equals CAT. Q equals big C delta T. Notice I'm not talking about the substance that's doing the heat exchange. I'm talking about the container itself. Okay, so this is for container only. So write down what you need to there, and I'm going to tell you a little bit more that I missed here. So generally in these forms of questions, it'll say the calorimeter has a heat capacity of 1 joule per degree Celsius. So basically, all that temperature change that's happening inside, let's say it raised by 10 degrees on the inside, for every 1 degree it increased, the coffee cup calorimeter is also absorbing 1 joule. So if I define big C as 1 joule per degree C, and I raise my temperature of my system by 10 degrees Celsius, how much is my container absorbing? 10 joules, because it's 10, it's Q is equal to 1 joule per degree C, which is what I define big C as, and the whole container, the system increased its temperature by 10 degrees Celsius. So the calorimeter, which we always label our Q as Q calorimeter, and so 1 times 10 is 10 joules. I'm saying the calorimeter is absorbing 10 joules, which we have to count for when we do our true heat calculations. I see confused looks, so just trying to see where we are. Ask me a question, or clarify what I've just said, or tell me, does this make sense? It does make sense? It's a big C. Please be big or little, like no like medium C's. Okay, big or small. Okay, so if I have a calculation that says what the heat capacity is, and you have information about the stuff happening inside of the container, like, oh, it's mass and it's temperature change and it's water, maybe you have your own specific heat capacity, your total Q will be Q of calorimeter, which you calculate by Q equals equal to CAT, plus your Q of system. It's summative, right? Because the Q exchange, the heat exchange, is not only what you measure with your thermometer, which is MC delta T, it's also what the coffee cup itself is doing just by chance, because it is a container that has the ability to absorb just a little bit of heat. So make sure you're summing those in the end. Yeah. And this would be like what true, well, it depends on if this is from measurement or if this is from a standard.
Or from so we'll be given the
Heat capacity?
heat capacity of those coffee cups. That could be like.
This could be theoretical then. But if I asked you to find your own heat capacity of the cup, it would be experimental because it would be from data collected. So it depends on the situation, right? Okay, so let me pause for a moment.
you guys have your subset of questions in front of you. I'm going to leave you alone for now, but I've got some more enthalpy stuff to talk about tomorrow, so just know that for the first 2 days of this, we're going to be talky. So you guys have your star ones you're doing for your work and heat, doing your work and energy, and then you have 1 through 6. I still want you to try 1 through 6. We didn't get through the last example I need to get to, but I think you'll be okay. Let me see where we are. You're doing 1 through 6 on the heat transfer concept. Heat transfer concept. And I just did number 1 for you. Yes? You see it on there? That's number 1. You're finishing the stars on the left, and you're doing 1 through 6 on the right.